You guys are way past the midpoint. So if you made it this far, you're like basically home stretch, like for physics 141. So on that note, yeah, I think that's it for announcements. And now let's see if I can find my beautiful, maybe not so beautiful whiteboard. Trying to remember what we're lecturing about. Okay, so we're continuing on the topic of statics, what I call statics. And these are basically finding equilibrium states. And by equilibrium states, we mean the sum of all the forces on something is 0, and that means there's no acceleration. And that's true for every piece of the system. And the sum of all the torques is also 0, so that there's no rotation, right? So by static, you mean no acceleration and no rotation, right? So both of those, no, yeah, no rotation, no angular acceleration. Torque really gives you angular acceleration. So so that's what we're going to talk about again. And so I was right in the middle of this example, and so let's do let me set up the example again. So you've got these two scales, and here's the scales, and then you put this beam on it, and we care about the mass of the beam. So the mass of the beam is mg, and I'm assuming it's a uniform density beam. So then you apply the force from gravity at the center mass of the beam, and then there's this box sitting on the beam, and it's at some distance L/4, and the beam has distance L, and the box has big M mass, and it's applying, it's applying a force on the beam there, and a quarter of the way down from the left end. And then I gave whoops, I don't want to put the coordinate system there. I'm going to put the coordinate system at this scale, so x, y, and then so we're looking at the forces and the torques on the beam. We'll assume that the box is like a point mass, and so the scale gives a force upward on the beam, so we'll call that FR because it's the right scale, and then the left scale FL. And so if we didn't have the box on the beam, then FL would be equal to FR because we've exactly balanced it, because the scales are touching the ends of the beam. But because the box is on is on top of the beam and it's not in the center, the force, the scale, it's like there's more weight on the left scale. So the point of this problem is to try and figure out what the scales would measure. So what do the two scales measure? So so that's the point of this problem. So so the first condition is just the force balance. So you just add up all the forces on the beam. So there are only vertical forces. So that's with my little coordinate system here, I have x and y. So all the forces, you look, the gravities are down and the scales are up. And so if I do force balance FL plus FR minus mg equals 0, and that's the condition for force balance. So torque balance, so we have two unknowns, right? So FL and FR. So we need at least two equations. Everything else we know. The m's, we assume the big M and little m, we assume we know, and we know what G is. And we assume we know L. So we have two unknowns, the two forces. That's what we're trying to find from the scales, which is the same as what are the scales measuring. So we need another equation. And so torque balance would be obvious. And you can say, well, where should I put the origin when I compute torque balance, and it doesn't actually matter. So if you could do torque balance with origin here, right on the top of this scale, or you could do torque balance here on the top of this scale. And what you'll find out is you get 3 equations, but they're going to be degenerate. So you don't actually get any more information. So I'm going to take torque balance from the left-hand side. And so let's do torque L. And so I need to do R cross F. So how many forces are on the beam? Well, there are 4 forces on the beam. There's the FL, and there's the big mg and little mg, and then there's FR, which is the other scale. So FL, so if I take origin right here on top of the left scale, then the radius to the point where the force is applied is 0. So there's no torque from that component. So the first torque component I get is from, so going out in distance from this the top of the scale, the first torque piece, piece would come from big M, the box, right? So the distance to the box is L over 4. So this would be R cross F, but I have to keep track of directions. So F is going to be mg z hat, and I need a cross product in here. So I didn't quite give enough room. So let's do it again with a little bit more room. So cross mg z hat with a minus sign, right? Because and why did I call it z hat? I drew a coordinate system with y up. So let's make sure we do this consistently. So we have mg minus mg y hat, because force is down. So that's the torque from the box. And now we do the same thing for the gravity onto the beam itself. So we have L over 2 x hat cross minus mg y hat. And that's the part from gravity onto the beam. And then the last piece is from the torque from the scale that's pushing upward on the beam. And that will be L x hat cross FR. And which direction is FR? It's in the plus y hat direction. So, and then we set this to be 0 because the beam's not rotating. And so let's rewrite this. So x cross y is, x hat cross y hat is plus z hat. So all of these have x cross y's in them, but they have different signs. So ignoring the z hat part, so this would be L m g over 4 with a minus sign, and then this one is minus L m g over 2. That's from the gravity onto the beam, plus L f r, and that equals 0. So this with this is 2 equations for 2 unknowns. And we can solve for both FL and FR, actually. And so let's do that. I'll just write down the solution. It's nothing hugely difficult to do. So FL turns out to be this, mg over 4 plus mg over 2, and FR is FL, it's minus FL plus mg plus mg. So we can find that. Let me just do that. So this is FL, which will be 1/4 mg over 4 plus mg over 2. So finding the solution. So looking at this, drawing this picture again, the box, gravity, you can kind of see that gravity is equally, of the beam is equally distributed, which kind of makes sense because it's, balanced. But the part from the box, because it's nearer the left-hand side, more of its weight winds up being distributed on the left scale than the right scale. So and so I could have given it a free parameter, like how far is the box from the end. And as you get closer and closer to the left scale, you're going to get all of the weight on the left scale. And if it gets closer to the right scale, all the weight's going to go on the right scale. And it's essentially linear, right? So so if we had done that as a free parameter, you would have found that it was linear. So so to just practice, let's see, we can go, whoops, I wanted to go back to this. And so if you wanted to, so with these problems, force balance turns out to be pretty straightforward. You don't have any choices. With torque balance, you can choose, where do I want to do this? Where do I want to put the origin when I compute the torque? And so I did torque on the left, but what if we had done to the right, use the right one, the right scale? We could have solved the problem using that one. And so let's write down, let me just show you how you do it. So torque on the right hand side. So so let's start with the box. We would have 3L/4 x hat, but now it's in the minus x direction. So there's a minus sign, cross minus mgy hat. And then we would have the same with the for the board itself, gravity from the board itself, but now it's got a minus sign because we're going that way, right? So we have minus x times minus mgy. And now the force from the scale on the right doesn't contribute because it's at the pivot point, but the force from the left scale does contribute. So you have minus L x hat cross FLY hat. And so, yeah, so we could have used that equation too. And you can solve the problem with both of these. You don't even need to use force balance if you want. You'll find out you'll get the same answer, which is, I guess, comforting. So, yeah, so you have more than one choice, but you'll find out that they're degenerate. But sometimes a particular choice may be easier to work with. So yeah, so that's just, compromise. Okay, so let's do another example of statics problem. Only this one, it'll be two-dimensional instead of, like the board one, all the forces were vertical. So, it was a little bit easier than if we had a two-dimensional system. So let's do this problem of a ladder against the wall. So I'm just describing it, but let's draw it. So we've got a wall and there's a ladder. Here's the ladder. And yeah, so the ladder is up against the wall and it's touching the floor. And so I'm going to give a coordinate system, X, Y again. And then let's call this H. And we'll call this A. And then, so we have various forces. Now we're going to put a guy on the ladder. So a guy is walking up the ladder. So my beautiful artwork here. We put a hat on him. Why not? So here he is walking up the ladder. And so he's exerting mg on the ladder, right? And as he moves up the ladder, so you think about this pivot point. Yeah, so what are the wall and the ground doing? So let's assume the wall has no friction, which is, not a great assumption, but it'll simplify the problem. So there's a normal force from the wall, and there's no force parallel to the wall if there's no friction. So we have a force Fn. So it's force wall normal. Because the wall pushes up against the ladder. So we will assume that there's a friction force from the ground, but there's also a normal force from the ground. So let's call it Fn normal. And then we have a friction force F ground. I think I called it Fr, friction force. The ladder can have some weight. So I'm going to assume the ladder's bottom heavy, and we'll put the center mass of the ladder there. And so I think, what did I assume? I think we put this distance at a/3. That's the distance of the center mass. And then the guy on the ladder, we put him at a/2. But as he climbs up the ladder, or she, because we actually have a demo for this, and you climb up the ladder and the torque, so because you get higher and higher, the torque around this point gets larger. And so that means the friction has to get, you have to have a larger friction force in order to keep the ladder from slipping. And this also depends on the angle of the ladder. Like, you know from experience that you want the ladder nearly vertical, otherwise it's more likely to slip. So as you go up the ladder, the friction force has to be higher and higher. And if you have the ladder tilted too far over, you can start to slip. And so we actually have this fine-tuned in the lecture hall, where as you climb up the ladder, you actually start to slip. And if you don't know better, you think you're falling. There's a bar that catches the ladder. But right now I'm not climbing any ladders anytime soon. So so too bad for that demo. Okay, so what are we actually trying to solve? Once again, we're trying to find the forces in the problem. And so we know big M and little m, and we know the distances A, and the distance of the center of mass of the ladder, and the distance of the person on the ladder from the end of the ladder. So we're trying to find forces. Find the forces from the wall and the ground. So those are 3 forces. So this would seem more complicated, but it's 2-dimensional. So we actually have 2 force constraints. So force, when you sum all the forces, you have an X and you have a Y component. So it's not as bad as it sounds. So we have 2 force equations for the X and Y components, and then you choose a torque constraint, like either from the bottom of the ladder or the top from the ladder. And it's a little bit harder to compute the torque, because now you're applying forces like gravity's down, but the radial vectors are along the ladder. So and we've got forces that are up, and we've got forces in the X direction and forces in the Y direction. So the torque constraint is a little bit harder to compute, but not significantly harder. So right, so what else do we want to do? Yeah, so sometimes it's we could, so I wrote A here as the distance along the floor, but if we have the distance of the ladder, it might be handy, to write things in terms of the distance of the ladder. But a squared plus h squared is equal to L squared. So you can always find A from the length of the ladder if you want. And if you want to, you can write this problem in terms of the angle of the ladder too. Okay, so let's start trying to solve the problem. So we're trying to find these forces. We need 3 equations to find 3 unknowns. So let's do vertical force balance. So that's Fy. So I'm going to add all the vertical forces. So I have mg, which is in the minus direction. That's for the center of mass of the ladder, the gravity onto the ladder. And then I have the guy climbing the ladder, that's big mg. And then what other vertical forces? Well, there's this normal force here from the ground. And this has to equal 0 in order for there to be force balance. So this we actually have one of the things we wanted to find. So Fgn is equal to mg plus mg. So we have one of our unknowns already with our first equation. So horizontal force balance. So let's do horizontal force balance. So that's Fx. We're going to sum all the forces on the ladder for the horizontal component. So there's the wall force over here, and then there's the friction force. So F wall and yeah, so you have to decide when you draw vectors if you're gonna when I drew the gravity ones, I drew them down, but then I assume that they're in the minus y direction here. So so you have to be a little bit careful, like how you decide, am I drawing the vector in some direction and I'm only talking about its length, assuming that it's got that sign associated with that direction or not. So here, even though I know the friction is going to be to the left, I'm going to let the sign be inside the force itself. So GFR equals, and the two have to be the same. So this is going to be negative. So just so that, so I know it's negative based on how I drew the picture of what I expect. So this equation, two unknowns, so I don't get any new information. So I need a torque balance equation in order to solve the problem. So yeah, I really need the picture. Wouldn't it be nice to have an extra blackboard here that you guys could see, because you need the picture in order to do it. So let's just do some erasing so that I have some room to do torque balance. Okay, so I need to pick a point. So I'm going to pick this point, this one here, to as the origin. We could pick a different point, like the other end of the ladder, but just pick that one. Why did I pick that one? Yeah, it's a little bit shorter because the ground forces are all zero, don't contribute to the torque. I mean, they're not zero, but they don't contribute to the torque because R is zero if the forces are exerted at the same point where you're computing the torque. So so let's do the torque balance. Let me do it in blue, not green, because it's kind of hard to see the green. So so let's start with this guy here, the torque from that. So so I drew my coordinate system, so positive x is to the right. So so the x comp, so taking this over here, the torque, gravity is down, right? So I don't care about the y component of the vector. So the vector I want is this. So that's r, and this is f. So r cross f when I compute the torque. So I don't care about the y component because the force is in the y direction. So I only need the x component. So I'll just write down the x component, which is a over 2 with a minus sign, x hat cross minus mg y hat. So that's the contribution to the torque at this bottom point of the ladder from the gravity force on the person climbing the ladder. Okay, so let's now do the force from gravity from the ladder itself. So that will be R cross F here. So we have minus A over 3 X hat cross minus mg y hat. So that's gravity on the ladder, what torque it gives. And then we need this R is going to be this, and F is going to be that. So let's choose another color here. I should have drawn it in green. So I only need the, oh, right. Now the force is in the horizontal direction. So I need the vertical component of R, right? So I have HY hat cross FWN X hat. There. So x hat cross y hat is z hat. So let's just figure out all the signs for everything. So this, let me put it in blue again. Could you please, we have a question. Could you please explain this last part that I drew in green? So R is here and F is here. And when I compute R cross F, the force is only in the horizontal direction, that's in the X direction. So I don't care about the X component of R because X hat cross X hat 0. So you only care about the perpendicular components. So I only took the vertical part of R, which in this case is H, right? So this is the vertical part of R. So I could have written this out in more detail. So let me show you how I would have done it in more detail. Oh, is that okay? Because we could do it. I could do this. It's actually HY hat plus minus AX hat. So that actually is the full vector cross FWN X hat. But this cross that is 0. So I can just get rid of it. And so I only kept the Y component. It's just a little bit shorter. Good, thank you. Good. I'm glad that's clear. Okay, so let's now write these terms. So we have AMG over 2. We have 2 minus signs, so they cancel out, plus AMG over 3. That's the second term. So yeah, so I'm tempted to just do HFWN. That's the normal component of the wall force. Why does the ladder rotate around? Let's get the rest of the question. The center of mass in this situation. So the ladder doesn't rotate around the center of mass. This is just when you're computing torque, you take with gravity, you can apply it at the center of mass point. So we showed that at the beginning of this set of lecture notes. And so when I'm figuring out what the force from gravity is on the ladder, I put it at the center of mass. In this particular problem, we kind of arbitrarily put the center of mass a little bit low on the ladder, like we pretended the ladder is somewhat bottom heavy. So the ladder is not actually rotating around its center of mass. What happens is if the friction force is not strong enough, the ladder starts to slip. So remember, the friction force is at most a friction coefficient times the normal force. And so once we find the normal force, so when we solve the problem, we can solve for the normal force, and we're going to solve for the friction force. And if the friction force winds up being bigger than the friction coefficient times the normal force, then the ladder slips. So that's essentially, but first we set up the whole problem with, where the person is and what the angles are and what the distances are and everything. And then we ask, what do those forces have to be in order for this to be static? And then if the friction force has to be too big, then the ladder has to slip. Does that kind of make sense? I mean, once it slips, the ladder rotates, but then it's a dynamic problem. If you want to compute the dynamics of that, then we would have to, actually compute the torque and everything. Okay, so what I was trying to do is now figure out the torque. So we have Y here cross X, and remember X cross Y is equal to minus Y hat cross X. So there's a minus sign here because we have YX. All the other ones are XY. So, and then this is equal to 0 because we need torque balance. So, so this means actually we can solve for this. And previously we had a constraint that related the friction force to the normal force. So let's write down, we have wall normal has to equal AM. Actually, it might be nice to write this a little bit. M over 2 plus M over 3 times AG, right? And then we had a constraint before that the friction force is plus the normal force. They have to be the same thing. So that was from the force balance equation. So this means we have so this is the ground friction force has to equal the negative of this. And so now we know this. So we've actually solved now for all three forces. So we've got the friction force, we've got the wall normal force, and we found the ground normal force previously from the vertical force balance equation. So so let's why don't we divide? Oh, right, there should be an H. Yes, there is. I lost an H. There is an H. Thank you for finding that. Yeah, don't forget this H over here. There is an H. Okay, so yeah, so we can now ask, so we found the friction force and we found the ground friction force and the ground normal force. So we can take the ratio of the two of them. And so let's do that. So the ground normal friction force divided by the ground normal force. One of them is negative, but we'll just not worry about that. So I'll just put absolute value signs. And taking the values that we found, we get this. And then this is M plus M G. And so in friction problems, remember the maximum. So friction force has to be less than or equal to a friction coefficient times the normal force, right? So this has to be that, where this is the static friction coefficient. So this depends on A. So if you have a larger A, so remember, think about this ladder, here's A and here is H. If you, and this in fact involves A over H. So, as you tilt the ladder over, this thing gets larger and larger. So it gives you this feeling, it's like the more tilted over the ladder, you're more likely to slip. But this actually gives you a condition for, how far over could you go if you knew the friction coefficient. So if it's more tilted, then it's more likely to slip. So this is not counterintuitive. If you know for sure, I mean, if you ever set up a ladder, you don't want it too far tilted over, right? You want to have it pretty nearly vertical. Although you're also making sure you have a nice, strong friction, base, making sure there's no way it can slip. Okay. So, yeah, so the other thing is, what else can we do? So the person in this problem, when we did this problem, we put the person halfway up the ladder, but you can ask, well, what if I allow the person to start moving up the ladder? And so this half gets bigger and bigger as the person gets larger than a half as the person gets past the halfway point. And so you can replace that half with the fraction of the distance that the person walked up the ladder. So supposing I put alpha here, which is the fraction of the distance that the person walks up the ladder. And now again, you can see that this top part gets larger the further the person walks up the ladder. So you can imagine that the friction, you're more likely to slip when you're up high, right? So higher, so if the person is higher up, then also more likely to slip. Again, not counterintuitive, but you can actually, if you knew all the friction coefficients and things, you could calculate. So that ends this example of the person walking up the ladder 2D torque balance problem. So problem set has a bunch more like this, and why the person falls. Oh yeah, the person, it's not so much that the question is, why does the person fall? So when we calculated the problem, we assumed the person was halfway up that ladder. So there was this factor of 1/2 in there, but we could have redone the whole problem with saying, what if the person is alpha fraction up the ladder? So alpha is 0 when he's at the bottom of the ladder, alpha is 1 when he's at the top of the ladder. And then when you resolve the problem, you just wind up with alpha here. And then as you see, as alpha increases, this condition, in order to keep the ladder from slipping, this whole thing here has to be less than mu. But this thing on the left gets larger and larger as alpha increases. And so, so if you were just barely not slipping when you're at the bottom of the ladder, as you climb up the ladder, you'd slip, right? So there's those two limits. As yes, right. If you get larger than mu, then the ladder, base of the bottom of the ladder starts to slip, which means the friction is not strong enough to keep the ladder from slipping. Does that make sense? Okay, good. So that's the issue. So we just combined the static problem with a friction, a little bit of reminder on how friction works. Okay, so we have rotational stability, but we have toys and blocks and stuff. But I'm going to jump and then come back to these problems. And the reason is it's really important for you guys to look at harmonic motion near a stable equilibrium point, because we have a bunch of problems on the problem set that do that. Okay, so we'll come back to statics and we'll talk about blocks on blocks and torque balance for a pendulum and roly-poly toys and other fun things. But let's go ahead for the moment. So we're doing statics, which is equilibrium, right? So equilibrium. So what is equilibrium? So I'm going to talk about in 1D. So supposing in 1D, I have X and I have some force on this problem. X dot is 0, that's a velocity, and we have X double dot is equal to 0. So there's no motion. So this is equilibrium in 1 dimension. So when people usually talk about equilibrium, it means, yeah, it's a steady state. So for dynamical systems, you've got some dynamical. What's a dynamical system? A dynamical system is something that obeys some equation that looks like this. So this is dx dt is equal to some function. But for us, when we talk about a particle moving in 1 dimension, it's a little bit, we actually, so maybe I shouldn't have used X here. Let's use a different symbol here for what's called the dynamical system. So dynamical system, we'll call it Y. So it's dy dt is equal to some function of Y. And then an equilibrium point is dy dt is equal to 0, which is equivalent to saying f of y is 0. But in this problem, which is this physics problem of a particle moving in 1 dimension, we actually have both the velocity and the acceleration equals 0. So there's an easy way to generalize this, still a dynamical system, but we just take y to have 2 components, actually. Why won't this erase? Y is equal to x and x dot. So it's got 2 components, and then dy dt is equal to x dot and x double dot. And then we have a function of this vector, which has got these two components. So this is position, and this is acceleration. Oh, that's velocity, not acceleration. And when I take the derivative of this vector, I get velocity and acceleration. And that means my function is a function of position and velocity. So you can talk about, for a one-dimensional system, you can talk about what's equilibrium as just a condition on both of these things being constant. So there's nothing particularly weird. And then if you want to put it in the context of what's called the dynamical system, you can. So I'm only mentioning this because it's like this big field, I guess you could call a field of applied mathematics on dynamic systems. It's really got lovely complexity in it. So, it's cool. But there's also some nice classes at the university on it because there's an expert who works on dynamical systems in the math department. He gives beautiful lectures. Okay, so right, so let's go back to the physics of this problem. So I'm going to look at a potential. So remember we had harmonic oscillators. So let me actually draw a harmonic oscillator. It's not a complicated potential. We're going to draw a harmonic oscillator. So we have a potential in 1D. And for a harmonic oscillator, it looked like this. This is a harmonic oscillator. So, so force is the minus the derivative of the potential energy. And so mass times acceleration is equal to the force is equal to minus d dx of u of x, which, so if I take the derivative of a harmonic oscillator, it's going to be minus kx. So, so let's look at the bottom of this problem. So where is the acceleration 0? So acceleration at x equals 0. And then we have to have velocity equal to 0 too, in order for it to stay at the bottom. So I don't know if you guys remember from earlier, if we, you can write energy is equal to the kinetic energy plus the potential energy. And so if I assign an energy up here, then a particle moves back and forth in this potential well, and at this point the energy is equal to the potential energy, but at this point the potential energy is 0, and so the energy is equal to the kinetic energy. And so there's like, it goes back and forth between energy being kinetic energy and potential energy. But at the bottom, if you start off the particle with 0 velocity, so x dot equals 0, and at x equals 0, then it stays at the bottom of the potential well. Okay, so for the harmonic oscillator, we know that x dot equals 0 and x equals 0 is an equilibrium point. Means the particle stays there forever. Okay, so what I'm going to do now is to say, well, this is, this would be, we already know this would be true for any potential energy if you start down at the bottom of one of these places. So let's take a more complicated potential energy function. If we put a particle at the bottom of a potential well and we put the velocity equal to 0, it'll stay there. So, it's not going to go anywhere. And same if I put it here. If I put it here at the top, it will also be an equilibrium point. But if you move it very slightly away from that equilibrium point, then it will start to, leave. So these points are stable. Point. And this one is what we call an unstable equilibrium point. So I probably mentioned this before, but stable in this context means if you start the particle very slightly away from the stable equilibrium point, it doesn't leave. It doesn't go very far away. It just stays in the local vicinity. So, so now what we're going to do is say, let's suppose we're at an equilibrium point and particle never leaves. It's very close to the equilibrium point. What's the motion like near the equilibrium point? So that's the question. So we're going to assume we're really near one of these stable equilibrium points. So another way to say that is, so I'm kind of going to give you the answer: harmonic motion at the bottom of a potential well. So this is more like what a physicist would call this. So the answer is it's going to be harmonic, which means it's going to look like a harmonic oscillator. And when we talk about our potential, whatever it happens to be, we're going to be near the bottom of, so when you say it's a potential well, it means that you're at the lowest point in some potential. I guess this whole thing would be called a potential well. Okay, so what I'm going to do now is show you that you do in fact get harmonic motion if you're near this equilibrium point. And so what we're going to do is take our potential function. So we have a potential function, and here's the stable equilibrium point that we want to know what the motion looks like when we're near it. We'll say it's at x star. So x star is the equilibrium point. So this is the x-axis. So we're going to expand around x star. So x star is the equilibrium point. So at the equilibrium point, you have to be, the curvature has to be 0. So there's no force. So du dx at x equals x star equals 0. That's the condition to be, when the slope is 0. So notice the slope is 0 here. That's a condition for no force so that it can be stable. So this is true at x star. So yeah, so let's expand. So what you do is you use a Fourier, not a Fourier, you use a Taylor expansion, and we're going to Taylor expand around x star. So let's do that. I'm going to get some space here so that I can do that on the same. So u of x is approximately u of x star. So I'm expanding around the equilibrium point plus du dx evaluated at x equals x star times x minus x star. This is a Taylor expansion, right? Which hopefully you've seen in calculus. And this is at x equals x star. And then we have the distance squared like that, plus higher order terms. So this is 0 here. By definition, that x star is an equilibrium point. And this is a constant, and this is a constant. So let's make a new variable, like y is equal to x minus x star. Then y double dot, so this is a constant, it's just a number, y double dot is the same thing as x double dot. And u of x, u of y is a constant plus this thing, which is 1/2 d squared u dx. Oops, I don't want to use partials because we're only working in 1D. X squared at x equals x star of y squared. So let's call this thing k. Okay, so let's write this out. So we had x double dot is equal to minus du dx. That was our previous equation of motion. This is going to become y double dot, and this u near the equilibrium point looks like a constant plus 1/2 ky squared, where k is d squared u dx squared evaluated here. So this means I can write this as y double dot is equal to minus du dy. And u is a constant plus this thing. Like that. So notice u looks just like a harmonic oscillator. So when you expand to second order, so second order means from the distance from the equilibrium point, then u from an equilibrium point, then what you get is you get a quadratic function. And you just have to remember that harmonic oscillator has a quadratic function for the potential energy. And so that means that you get, essentially, you get harmonic motion near the equilibrium point. So many of us have not seen expansions in calculus. Well, yeah, I know. So you get to see it first in physics. I'm not sure if that cheers you guys up or not. But let me like, to make up for that, let's talk about what it actually means. So what it actually means is, so for any curve, right? I have a constant, and then I can take a line, and then I can fit some curve thing to it. So Taylor expansion is just progressively doing polynomial fits, polynomial fit to a curve. And here, because we're at the equilibrium point, there's no linear term in this because the derivative is 0. So really, it's like we're approximating the bottom of the curve with a parabola. So, so I have a complicated potential. So it's approximating the bottom of the potential well with a parabola. And that's just, so it's kx squared. And when you put the origin there, it just looks like 1/2 kx squared. And and that k is just the second derivative of the potential evaluated at the equilibrium point. So but what's the take-home story here? So the take-home story here is that if you are at the bottom of the potential well, you don't go very far away, then the motion is similar to that of a harmonic oscillator, and the spring constant just depends on the second derivative. And so, that means you can find the period of oscillations, and, everything that you know about a harmonic oscillator. So this, again, the harmonic oscillator just permeates physics. It's basically everywhere. And so this is another way that it comes into physics problems, where you look at behavior of things at the bottom of the potential well. So you see this in quantum mechanics too. So molecular spectra, spectra of molecules, for example. Lots and lots of settings. So harmonic oscillator is like again, in like physics, it's like harmonic oscillator is one of the few solvable problems. So that means everything, if you bash your complicated problem, make it look like a harmonic oscillator, then you feel good because you can say something about your problem. So it's like kind of on this theme. So let me summarize what's going on with this. So if we have a stable equilibrium point, then yeah, so let me just summarize. I need to go back to the beginning. Share, and we'll start share again. So if you have a stable equilibrium point, and a potential energy function, and so your stable equilibrium point is x star, then you near the equilibrium point looks like this, plus 1/2 k x minus x star, and k is like in a spring constant is this thing. It's evaluated at the equilibrium point. And if you have a mass moving at the bottom of this near the stable equilibrium point, then the equation of motion looks like this. The minus sign y, where y is equal to x minus x star. And just like you have with the harmonic oscillator, the frequency of oscillations looks like this, and the period looks like 2 pi over omega, and the solutions are sinusoidal. So for any stable equilibrium point, if you have motion near it, you can figure out the period of oscillations. Yeah. So that's the how to figure out harmonic motion near a stable equilibrium point. So what are applications of this? So yeah, so let me so what next? Yeah, so this may seem archaic, like why do we do this? So let me give you an example of where it winds up being useful. So one previous lecture, we talked about Keplerian motion. And so with Keplerian, it's a particle in an orbit around a star. And we showed that there was if you took the two-dimensional problem and you made it look, you only think about the radial motion, there's this effective potential. So this is for radial motion in it's Keplerian. So this is orbit around a mass m. And so the effective potential depended upon the angular momentum, the orbital angular momentum, and it looked like this. And I drew a picture to show what this effective potential looked like. So if I draw a radius, once you choose the angular momentum, the effective potential, this is the effective potential, looks like that. It goes to 0 and infinity. And so this effective potential tells you, so the equation of motion for the radius, dr double dot, not double dot, it's just dr squared, dt squared is equal to minus du effective dr. So it actually tells you the equation of motion for the radius. So just like we did with this more abstract or generic problem, you can look at, all right, what's at the bottom of this potential well? And when you're at the bottom of the potential well, there's no kinetic energy. It's a fixed point. It's an equilibrium point in radius. So what does it mean to have fixed radius? Well, that's a circular orbit. So fixed radius is equal to a circular orbit in this setting. So I can find, if I take the derivative of this equation, du effective dr is equal to 0, I can figure out what radius gives me a circular orbit. So let's do that. I can take the derivative of this function. It's minus L squared, I need a 2 there, over 2r cubed plus gm over r squared equals 0. And now I can solve for r. So let's do that. Well, I'm going to need to do a few steps here in order to get this right. So get rid of these 2's, and then I have L squared is equal to gm r, right? Yeah, that looks right. And so r is equal to there's no square root, right? R is equal to L squared over gm, right? So this is r star, which is my equilibrium point. I even got that right. No mistakes. Good. Awesome. So, well, now I can say, well, what's motion like around the equilibrium point? And so these are radial. So we can think of the orbital mechanics as radial oscillations near the circular orbit. So what does that mean? So I have a circular orbit, and I'm just assuming that I have very slight oscillations around the circular orbit. So this would be if radial oscillations were quick compared. So that here I drew many wavelengths around the circular orbit. So for the Keplerian system, the actual orbits are ellipses. So actually, when you think about what does a radial oscillation look like, it's like this. So on one side, it goes to a higher radius, and on the other side, it's a smaller radius. But basically, just the radius is doing a small excursion from the radius of a circular orbit. So here's the ellipse. So there are settings where you get orbits that look like this, actually. So maybe not like this. You can make Keplerian systems sometimes like this if you work in a rotating frame. But more commonly, like in a galaxy, you don't have elliptical orbits. In a galaxy, what happens is, so here's a circular orbit. So the sun is actually not, and when it orbits the galaxy is not exactly in a circular orbit. It has small oscillations around the circular orbit. And what it does is it does stuff like this. And you get what's called a rosette, where the period of the epicyclic oscillations is larger than the whole, the frequency, the period is longer than the time it gets to go around. So it takes longer, you do one oscillation in more than an orbit period. So so that's why you get this thing that looks like, what was that? So going back to our previous page, we found the r star, which is the radius of the circular orbit. So now we can look at the potential and just expand around that point, that radial point, and that will give us the frequency of radial oscillations. So I guess we can go back and do that. So if we have U effective is L squared over 2r squared minus gm over r, and then I just take the derivative twice, 2L squared over 2r cubed plus gm over r squared, d squared u over r squared. Now I have to take the derivative again, minus 3 with a plus 3 over r to the 4th plus, now I have to minus, because derivative of 1 r squared is negative, minus 2gm over r cubed. And then this is r to the 4th. And then I need to evaluate this at R star. And remember, R star was L squared over GM. And when you do that, what you wind up with is, so this is what we call K kappa squared. And it's the, another word for it is actually the epicyclic frequency. And so when we do that, you get 3L squared over R star to the fourth minus 2 minus, come on, minus 2GM over R star cubed. And so if I actually evaluate it, like I put R star in there, what you wind up finding for Keplerian orbit is that the epicyclic frequency is equal to the angular rotation rate for the orbit. Kappa is what's called the epicyclic frequency. Equals the angular rotation rate. And that's necessary to get an ellipse. But if you substitute it in, you'll get that. So this is an application. It's like a simplification. And if you want to approximate near, use the fact that you have a potential well to make an approximation at the bottom of the potential well to say something about the dynamics. So that's kind of the point. Go beyond the static setting. Okay, so we have a little bit of time. And so I think, why don't we talk about toys for a little bit? So, yeah, so let's talk about rotational stability. Stability, there we go. So here we have like some pendulum system, but the center of mass might be out here. X center of mass. And if we have gravity, then here's a pivot point. Then in order to have this thing in a stable setting, torque balance winds up being X center of mass, which is this vector, cross Z hat has to equal 0. So when you have R cross F, because when you have gravity exerted on a system, you can always approximate it like it's as if that gravity force is applied at the center of mass. And so the torque balance is winds up being, you just apply the force at the center of mass position. So what does this mean? So what this means is, the way I've drawn it here, the center of mass is to the right and gravity's down, so the whole system is going to tilt down. So the condition for it to be stable is you have to have the center of mass above or below the pivot point. So for equilibrium, the center of mass position either above or below the pivot. So if it's above the pivot, it's still an equilibrium point. It's like having this upside down pendulum, but it would be an unstable equilibrium point because if you nudged it, it would start to fall over. And if it's underneath, then it would be stable. So if you nudged it, it would start to oscillate like a pendulum. So, so that's a condition for rotational stability of something with a pivot. So what about like a roly-poly toy? So a roly-poly toy is what they look like. So what a roly-poly toy typically looks like inside is it's mostly empty. And here you put it on the surface, you put it on a flat surface. And the center of mass is typically you know, it's very slightly above where all this mass is. And then if you tilt it over, here's the tilt it over, then here's the contact point. And if the center of mass is above the to the right of the contact point, then it will tilt over. So if you put this, if the center of mass, so here it's draw, the center of mass winds up being really low, and then that means that the contact point can be really far over before the center of mass winds up to the right of the contact point. And so it will then, even when it's quite tilted over, it will be stable. So yeah, so that's what's going on with the roly-poly toy. So this comes down to figuring out when is the center of mass above or to the right or to the left of the contact point. So you design, make the center of mass really low, and make the surface of the object curved so that it, it has to get really far over before the center of mass is above to the right of the contact point. So one bizarre thing is this roly-poly toy, obviously the mass distribution inside is not homogeneous. So it's like mostly empty and it has a lot of mass at the bottom. But it's an interesting question, is like, can you make a roly-poly toy that has a homogeneous mass distribution? So this is a really weird little curiosity. So I thought this was kind of cool when I noticed it. So it turned out Arnold, who's was a very famous mathematical physicist. So he's the Arnold from KAM theory, which is this chaos theory. He's the A in that theory. But he conjectured in 95, it's not that long ago, that there might be a class of homogeneous. So that means like even density convex. So convex means if you draw any 2 points on the surface, all points along the line are within the surface. So that there's a class of homogeneous and convex objects that only have one stable and one unstable point of equilibrium. And so he just made a guess, a conjecture is kind of a guess. But it turns out that in 2006, I think were they Hungarian? In any case, these two guys, Domokos and Farkoni, actually found a mathematical solution that obeyed this. And they're really weird looking. So I would encourage you to take a look. They called them gombach, I think. They're very strange looking objects. And it's very unlikely that anything in nature would do this. So one of the things they did is they went to beaches and measured tons of rocks and tried to see if any of them naturally wound up in this type of shape. And the answer is no. So most things don't obey this. But in any case, curiosity, if for anybody who might be interested. So we'll end there, talk a little bit more about blocks next week, and then we'll start in on statistical mechanics. So we'll stop there.
Thank you.
Thank you.
Yeah.
Bye.